Welcome back to the deep dive. Today we are tackling a topic that it feels a bit like digging up the foundations of a skyscraper just to understand how it stays standing.
Right.
We're looking at the core ideas that shifted computer science from, clever coding to actual artificial intelligence.
It is a bit of a history lesson, yeah,
Mm.
but the kind of history that's still actively shaping our future. We are unpacking a seminal paper, Representation Learning, a Review and New Perspectives, by Yoshua Bengio, Aaron Corville, and Pascal Vincent.
And the thing that grabbed me right away about this paper is how it starts. It addresses what sounds like an absolute nightmare for engineers in the pre-2012 world. This feature engineering bottleneck.
It really was a bottleneck.
Yeah.
A huge one.
I mean, correct me if I'm wrong here, but for decades, AI basically meant a human sitting in a room, probably drinking way too much coffee, and manually trying to write code that defined what, the curve of a cat's ear looked like.
That's not far off at all. The intelligence wasn't really in the machine. It was all in the human designing the pre-processing. You had to take this raw, messy data and manually transform it into a neat little list of features that a simple algorithm could handle.
And if you missed a feature, the machine just failed.
Completely.
So the dream, and I guess the mission of this paper, is to figure out how to get the machine to do that heavy lifting itself, to move from just recognizing patterns, we point out, to actually learning how to represent the world on its own terms.
That is the core shift, from pattern recognition to representation learning. The goal is to build a machine that doesn't just memorize pixels, but learns to represent data in these abstract, useful ways.
And the authors have a key argument for how to do this.
Right. They argue that the system has to learn to disentangle the complex web of reality.
Okay, disentangle, that word comes up a lot. Can I push back on this a little bit? Because to me, looking at a picture is easy. I see a mug, I see a table. Why is it so hard for a computer to just see that? Why do we need to disentangle anything?
Because what you see isn't what the computer sees. You see concepts. The computer just sees a massive grid of numbers. Let's take the shadow analogy from the paper. Imagine a red ball on a table.
Okay.
Now you cast a shadow over half of it.
Right, so half the ball is dark.
To you, it's a red ball with a shadow. Simple. But to a raw computer algorithm, that shadow is a complete disaster. It creates a hard edge where there isn't one. It totally changes the color values of the pixels. It creates a fake shape that has nothing to do with the ball itself.
So if the AI doesn't understand physics, if it doesn't get that lighting is a separate thing from object, it might think the shadowed part is a completely different object.
Precisely.
Yeah.
A good representation is one that can separate or disentangle these factors. It needs to say, okay, factor A is the spherical shape, factor B is the red surface, and factor C is the lighting condition.
And if you can separate those, you can recognize the ball no matter what time of day it is.
Whether it's noon, dusk, or under a lamp. It seems so obvious to us, but that's because our brains have been doing this for millions of years. We're asking a math equation to basically derive physics from scratch.
Which leads to the big problem. If we aren't hand-coding the features, if we're not telling it, look for edges or ignore shadows, how does the machine know what to focus on?
Exactly.
I mean, if you just give it a million random images, it could learn anything. It could learn to track the static noise in the background.
And that is why we need priors. Since we aren't giving it specific rules, we have to give the system these generic assumptions about how our universe works. They're like the ground rules of reality.
Okay, let's walk through these. The first one they mention is smoothness.
Smoothness is the most basic one. It just means that if two inputs are very, very similar, the representation should also be similar.
Oh, okay.
If I show the computer a picture of a face, and then I show it the same picture but shifted one pixel to the left, the computer shouldn't panic and think it's a totally different concept.
Makes sense. Small changes in input equals small changes in output.
But smoothness isn't enough, because the world is jagged. That brings us to hierarchical organization.
This is the Lego block theory, right?
In a way, yeah. The assumption is that the world is compositional. Abstract concepts are built from less abstract ones. A sentence is made of words. Words are made of characters.
And characters are made of little strokes and lines.
Exactly. And this justifies why we need deep learning. You need layers to mirror that hierarchy. But the most important prior, and the one that really requires us to stretch our imagination, is the manifold hypothesis.
I remember reading this section. It felt like we suddenly jumped from computer science into, theoretical physics. Can we break this down without the calculus?
We can try. So, to understand the manifold hypothesis, you first have to visualize the input space.
Okay.
Imagine a space that contains every possible combination of pixels, every random static image, every possible picture of every possible thing.
That space must be just unimaginably huge.
It's essentially infinite. Now imagine walking through that space. Almost everywhere you look, you just see garbage, white noise, random colored dots. It looks like nothing.
Because most random combinations of pixels don't make a picture of a cat.
Correct. Meaningful data, pictures of cats, recordings of human speech is incredibly rare.
Yep.
It doesn't fill that whole room. Instead, it's concentrated on these thin, curved sheets that are just floating in that empty space.
Okay, so I'm visualizing this. The room is full of static, but floating in the middle is this sort of crumpled up sheet of paper, and on that paper is every valid picture of a cat that could ever exist.
That's the image. And learning a good representation basically means the AI has to find that crumpled paper in the dark room. It has to map out the shape of that surface. Those sheets are the manifolds.
And once it finds the surface, it can move around on it.
That's the key. If you move along the paper, along the manifold, you get valid changes. The cat rotates, or it changes color, or it closes its eyes.
But if you move off the paper,
Into the empty space of the room, you just get noise, garbage.
so the AI is basically playing a game of the floor is lava, the manifold is the safe furniture, and the rest of the high-dimensional space is just lava.
That's a surprisingly accurate analogy.
Yeah.
And this geometry connects to another prior, sparsity. Because that manifold is so thin compared to the rest of the space, for any given input, only a tiny fraction of factors should be active.
Right. If you're looking at a cat, the is this a truck factor should be 0.
It should be off, yeah.
Okay, so we have the ground rules: smoothness, hierarchy, manifolds, and sparsity. Now I want to talk about architecture. We mentioned deep learning earlier. The paper makes a very specific mathematical argument for why deep is better than just being wide.
Right, and this is all about efficiency.
Mm-hmm.
You could theoretically have one giant wide layer of neurons that memorizes everything,
Mm-hmm.
but it would be incredibly wasteful.
So depth is about feature reuse.
Exactly. The system recycles what it learns. Think of a combination lock, or even better, a password.
No.
If you have a password that is 4 digits long, you have 10,000 combinations.
Mhm.
If you add just one more digit, you don't add one more combination, you multiply the possibilities by 10.
Right. It's exponential.
That is what deep distributed representations do. By adding layers that can reuse features from below, you get this exponential power. A little curve detector in a lower layer can be used by the upper layers to help define an ear, a wheel, a cloud, or a letter C. You don't need to learn a separate curve for every single object in the universe.
That makes perfect sense. If you didn't reuse features, you'd need a unique neuron for every single specific object you might ever see, which is just impossible.
And as you go deeper, you get more abstract. But I want to pause on a distinction the authors make, because it's often misunderstood. It's the difference between invariance and disentangling.
I struggled with this one a bit. Isn't the goal just to ignore the stuff that doesn't matter? Like, if I want to recognize a face, I should just ignore the lighting. That's invariance, right?
That is invariance, yes. And for a simple classifier, that's fine. But for a truly intelligent agent, that's actually a problem. If you become invariant to lighting, you have effectively deleted the lighting information. You can't tell me if it was day or night. You've just thrown away data.
I see. You've blinded the machine to that factor.
Disentangling is more ambitious. It says, don't delete the lighting info, just separate it. Keep the information that it is dark, but store it separately from the information that this is Bob. That way you understand the whole scene.
So invariance is essentially selective ignorance, while disentangling is organized understanding.
That is a perfect way to put it.
Okay, let's open up the toolbox. The paper breaks down how machines actually learn to do this. There seem to be two main camps here: the probabilistic models and the direct encoding models.
Right. Camp A is the probabilistic approach. These models treat the world as a set of hidden variables that generate the data we see. A classic concept here is explaining away.
I love this term. It sounds like something a teenager does when they get caught sneaking out.
It's actually a logic puzzle. The paper uses the burglar alarm example. Imagine your house alarm goes off. That's the data. Now you have two potential causes, two hidden variables that could explain it: a burglar or an earthquake.
Okay. Both are bad.
Now, normally those two things are independent. A burglar doesn't cause an earthquake. But if you turn on the news and hear there was a small earthquake in your neighborhood.
Then suddenly the probability of it being a burglar drops to near 0.
Exactly. The earthquake explains away the alarm.
So even though the causes are independent, the observation makes them compete.
That's it. In this type of AI, features compete to explain the pixels. If one feature says, I see a vertical edge here, the other features say, okay, good, I don't need to worry about that part.
In this camp is where we find RBM's restricted Boltzmann machines. The paper spends a lot of time on these. They talk about energy. Are we talking about electricity here?
No, and this confuses a lot of people. In this context, think of energy as more like tension or incompatibility. The model imagines an energy landscape. Real data, like a clear photo of a dog, should have low energy. It's relaxed. It fits.
And fake data.
High energy. It doesn't fit.
Oh.
So the RBM is constantly trying to adjust its internal parameters so that real data sits at the bottom of the valley, low energy, and noise sits at the top of the mountain.
And you stack these to make a deep belief network.
Exactly. And that was the architecture that kicked off the modern deep learning boom around 2006.
Okay, so that's Camp A, modeling probabilities and energy. Now, Camp B seems a bit more blunt. The autoencoders.
Autoencoders are conceptually simpler. You have an encoder that maps the input to a code, and a decoder that tries to reconstruct the input from that code.
It's like a translator. English to French, then back to English.
Yeah, and ideally you get the same sentence back. But here's the trap. If the machine just memorizes the input, it's useless. It's just a photocopier. It hasn't learned anything about the structure of language or images.
So you have to make it hard for the machine. You have to break things.
You do. Which brings us to the denoising autoencoder.
And I have to ask, why? The paper says you take a clean image, you add noise to it, smudge it, black out pixels, and then you feed it to the computer. If I'm teaching a kid to read, I don't spill coffee on the book first, why does this work for AI?
That's a great objection. With a child, you're relying on their brain's pre-existing ability to find patterns. The AI starts with nothing. By corrupting the image, say, taking a 5 and rubbing out half of it, and then forcing the AI to reconstruct the clean 5, you force it to learn the rules of the data.
How so?
It can't just memorize the pixels because the pixels are wrong.
Yeah.
It has to say, wait, based on the pixels that are left, this looks like a 5. And I know the 5s usually have a curve here, so I will fill in that curve.
So it fills in the blanks based on its understanding of what a 5 should look like.
Exactly. It learns to pull the corrupted data back onto the manifold, back to that safe, crumpled sheet of paper we talked about. It learns a vector field that points from the bad, noisy data back toward the good, real data.
It's learning gravity. It pulls everything back to reality.
That is a beautiful way to visualize it, yes.
Speaking of visualization, we have to go back to the geometry for a second. The paper mentions tangent planes and local coordinate coding. I got a bit lost in the math here.
Let's just use the map analogy. The Earth is a sphere. It's curved. That's the manifold. But if you look at a city map, it's flat.
Right. I don't need a globe to find the nearest coffee shop.
That flat map is a tangent plane. It's a local approximation of the curved surface. So the paper argues that these algorithms are essentially trying to stitch together thousands of little flat maps to understand the shape of the entire high-dimensional world.
And this is why moving along the manifold is different from moving off it.
Yes. If you are on the manifold, the Earth's surface, you can move north, south, east, west. Those are valid directions. You end up in a new city. That's like taking a face and rotating it.
But if you move off the manifold,
Straight up into space,
yeah,
you leave the world of valid data entirely. You're just floating in the void of static noise.
so a good AI knows that north is a valid change, but up is impossible.
Correct. It captures the local directions of variation that actually make sense in reality.
So we have the theory, we have the manifold, we have the tools. Does it actually work? The paper lists some success stories, but looking at them now, they feel like ancient history.
They do, but they were the turning points. They mentioned Microsoft reducing word error rates in speech recognition by 30%.
Which is a lot.
It's massive.
Yeah.
But the big one, the one that really changed the world, was object recognition, the ImageNet competition.
The paper cites the drop in error rate from about 26% to 15%. Now, to a listener, that might just sound like numbers. Why was that such a big deal?
You have to understand what a 26% error rate looks like. At 26%, the computer is basically guessing. It confuses a muffin with a chihuahua. It's a toy.
Okay.
When you drop to 15% and subsequently much lower, you cross a threshold. Suddenly, the computer isn't just guessing anymore, it's seeing. That was the moment the technology moved from the lab to the real world.
And they also mention NLP, natural language processing, this idea of word embeddings.
This is the precursor to things like ChatGPT. It's the realization that you can map words into that geometric space we talked about. Cat and dog are mathematically close to each other.
And king and queen have the same relationship as man and woman.
Exactly. It turned language into math. And this enabled transfer learning, which is kind of the holy grail of efficiency. If you learn the manifold of the world, if you learn that objects have edges and shadows obey physics, you can apply that to anything.
You don't need to relearn how to see every time you look at a new object.
You've built a universal translator for visual reality.
That's the hope. So are we there? Have we solved it?
Not quite. The paper ends with a look at the grand challenge. Optimization.
The boss fight.
We have the map, the manifold. We have the vehicle, deep learning. But the road is treacherous. Training these deep models is mathematically very difficult. You get stuck in local minima.
Where the AI thinks it solved the problem, but it's actually just found a mediocre solution?
Yeah. It stops climbing the mountain because it found a nice little hill and thinks it's the peak.
Right.
And there was one final, very forward-looking thought in the conclusion that I think is worth chewing on. The idea of implicit representations.
This was the part that felt a bit sci-fi.
Usually we try to calculate the exact probabilities of everything, the math of the posterior. But that is incredibly expensive, sometimes impossible. The authors suggest that maybe we don't need to do the math.
What do we do instead?
Well, think about catching a baseball. If you were a physicist, you would calculate the wind speed, the gravity, the velocity, the arc. You would solve the differential equations to know where the ball will land.
I definitely don't do that. I just run to where the ball is going.
That is an implicit representation. Your brain has learned a functional shortcut. You don't explicitly calculate the probability distribution of the ball's location. You just learn a feature that answers the question, where should I put my hand?
So the future of AI might not be about perfect mathematical models, but about learning these smart functional shortcuts.
Guessing right based on intuition rather than calculating the answer from first principles. That seems to be the direction we're heading.
It's funny, we started with engineers handcrafting features, trying to force the computer to be smart, and we're ending with computers learning to develop their own intuition, just like us.
It brings us right back to that mission statement. The quest to disentangle the world is really the quest to build a mind that can navigate it.
Well, on that mind-bending note, we are going to wrap up this deep dive. A huge thank you to Bengio, Corville, and Vincent for this roadmap, and to you for helping us navigate the manifold.
Always a pleasure to explore the space.
Catch you on the next one. Keep disentangling.